Hello, 5, 10, 6, 10 people. We're going to try this one again. This is my second video for the complexity growth areas, solving problems and things like this. Second time here because, unbeknownst to you, I started recording this last time and the battery died partway through. Fun. I am now on wall power. So we will try this again on a new sheet of paper. So we start off. Last time we did ocean. So let's say this time, for instance, we're now trying to solve a fast Fourier transform. Now that requires us knowing something about fast Fourier transforms. And the basic idea of them is, let's say that I've got a bunch of data points that I stack up in a vector. And I got all these lovely data points that are connected, let's say, time or spatially. But for the sake of argument, let's just say that these are a series of data samples in time. So this is time domain, and I would like to switch them over to take a look at what's happening inside the frequency domain. Now, the reason why we want to switch to frequency domain is because a lot of problems become much simpler inside the frequency domain. This is the nature of the Fourier transform, essentially like convolution becomes multiplication and so on and so forth. It also actually turns calculus problems into algebra problems. And so this is part of why it's so lovely as it goes. It turns, for instance, integration into division by your frequency, with, of course, a factor that has to do with the square root of -1. But, essentially you become a division problem. So, fun stuff like that. Derivatives become multiplication by j omega, so on and so forth. So, in any case, my point of this is that it simplifies a lot of things, and we would like to solve some problem, let's say, and that requires us to do a Fourier transform to solve this much simpler. Now, the fast Fourier transform is a divide and conquer algorithm. So the second you hear a divide and conquer algorithm, you should be thinking that it's going to have a complexity that's related to n log n with whatever it does computationally. Now, that is absolutely true, and it's a nice simple way. Let's say we were then going to take all these computations and split them up. Now, essentially, since it's log n number of steps on n data points that's going on, if I have p processors, then just, I'd have n over p on each one, and they'd still have the log n steps that I'd have to do. So I end up with that being my complexity on a particular cluster that has, let's say, p processors. Now the question is about how do I do communication. Now communication, and actually let me just do a real quick little example. There's a lot of ways you could do this, but I'm going to just show you doing what's called the butterfly example, where essentially you group them into, say, 2 data points together. And each one of these, there's a scaling on each line that goes in. And so these 2 data points generate these 2 as you're moving towards it. And then you have other ones that are doing the same exact little butterfly switch. And then what happens as they go on here is then you go between the different layers. So then you have, these 2 here. We'll then calculate, and these 2. And so on as you keep going up. So you get all these lovely crosses. Now, if you think for a sec, if this was on one machine and this was on the other, in order to do this computation where this one uses this one, I'd have to transfer one of them. Transfer this one down, and then proportionally I have to switch that one up. So essentially half of my different data points are moving at any one given time. Now, if I had a whole bunch, like 4 of these were sitting on here, I wouldn't have to transfer these. I'd have to transfer them at the stages when they go. So based on the number of iteration runs that are going in, it's actually proportional then to n over p, dealing with how many processors I have to go through. So we're going to take these as our basic areas, walking through it. We've got an idea of basically how our communication and how our computation scales. And so from there, what we can do is still work on it. Now let's imagine that I wanted to solve a fairly decent sized point, and let's pick a decent sized number. Let's say I wanted to deal with 2 to the 32 points. That's equal to my n. And I've been told that essentially I can have, let's say somewhere a little bit over an hour, like, an hour and 20 minutes in order to solve this problem, something like that. And I need to know how many processors do I have or do I need to get in order that this can be solved on a particular cluster that we set up in whatever, somewhere, say, 1 to 1.5 hours. Now, FFT is fairly quick and stuff like that. That is why it is called the FFT. But we still have to be able to get some estimate on these. We'll probably be measuring our things in seconds initially because we'll be dealing with smaller ones that go on. Now, it turns out when I did that Scilab example, when I went back to look at it, that's the numbers that it was spitting out on the side. You could hear me say them, but you couldn't see them, and it was kind of hard to read the code. So I figured this time, instead of doing it in Scilab, I'll just do it by hand. Now, that essentially means that, if you were going to do this, you'd have your calculator or whatever. But you can actually solve a lot of these by hand. And I do suggest, actually, that you get used to being able to solve some things, what we call pencil and paper style. Now, so we're going to move a little bit further down my page. Use my lovely analog computer here to move up. So if I was going to solve this and try and figure out what P is, I have to first of all be able to estimate what these different parameters are to pick them. So I've got to figure out that lovely alpha communication and computation. So what I would do is I would pick something. Now, let's say I had existing a cluster with 16 computers or nodes in it. So let's say I know, or I have access to a system where P equals 16. Now, it might be worthwhile for me to do some at P equals 4 and, 16 and maybe some other sizes, maybe P equals 8, assuming that that's my limit of computers. I might do on smaller ones so I could test the scaling. In reality, I wouldn't just take 2 data points either. At each time period, instead of just taking 1 point, I'd do a whole bunch, and then I'd go in and least squares fit these or something of that sort. But I wouldn't spend inordinate amount of time. It'd be pretty easy to measure it on a couple different sizes and get some times so that I could be sure that I didn't happen to just hit the time when some nasty little cleanup was going on, or my disk was setting. And you'd have to make sure that the problem is reasonable enough in size that it's going to hit problems with cache and other things that are similar. And this is a worthwhile mention. This is not really counted for in this type of a scaling here, so you have to account for it yourself. At different sizes of n, different issues come into play. So if your stride is big enough and things, you can run into cache problems. But if your problem's small enough, it might all fit in cache, and therefore you don't see that. So there are constraints that are not so easy to see without actually going in and working on them. So I'm going to pick for my test cases some ones that are not anywhere near as big as 2 to the 32nd, which would kind of fill up RAM on a modern system, but actually would still be of reasonable size, although not gigantic. So let's assume that initially I'm going to test it on n equals 2 to the 16th. Now, the reason why I'm picking powers of 2 is because FFT works most efficient on powers of 2. So if you're going to solve something, usually you even pad it in order to make 2 to the 16ths. Decent systems like FFTW and things like that will often handle this type of things for you. But, let's assume that we know what we're doing, and so we decide that we're going to set this up as a power of 2 ourselves. So given this, I find out I've got my P and my N, so I say, lovely, this gives me my n log n over p to be equal to the log. All logs are equivalent, and in this case log 2 is the one that makes the most sense, so that's the one that I'm going to use. So that makes it n is 2 to the 16th, and log n, log base 2 of 2 to the 16th is 16, and I divide by p, which is 16, so I just get 2 to the 16th here. Now, we also have n over p. That's my computation. This is my communication. This one is just 2 to the 16th over 16, which is just equal to 2 to the 12th. All right. So that gives me my factors for those. And let's say that, I also want to consider this same thing at, say, p equals, or keep p at 16, and let's say I also want to do this at, let's say n equals 2 to the 20th. We'll make it a little bit bigger, but still not horribly different. So in this case, that would mean that I would have n log n over p would just be equal to 2 to the 20th times 20 over 16. And so that is going to give me 2 to the 17 times 10, something like that. 2 to the, well, we could do it this way, 2 to the 18 times 5. And then we got n over p is equal to, and I've got 2 to the 20 over 16, which will just give me 2 to the 16th. Okay, so now we've got these things calculated up, nice and simple, and we want to pick some time. So let's say that I ran this one and it ran a little bit over a minute. So let's say it ran like 68 seconds. And let's say I ran this one and it ran, somewhere, it's like in, 22 minutes or something like that. So, it's a significantly bigger problem, by a factor of about 16 times. So it should be, that's a little bit over a minute, so we'll pick 20, 22, something like that. Putting that into seconds, a little bit over 22 is, say, about 1344. So these are, again, times in seconds to run them. So I would set this whole thing up. So I'd say, I got 68 and I got 1344. And for this one, I've got my 2 to the 16th. That's my computation one. And this one has 2 to the 18th times 5. And then I've got over here 2 to the 12th. And here I've got 2 to the 16th. And then I've got to take this is my alpha computation. This is alpha communication. I don't feel like writing them all out, so I'll just take the unique letter. So I've got alpha P and alpha M. Now again, I got to do my solving on there. And this one, like I say, it's easiest, just stick those in and calculate them off. So I have stuck this in and calculated inside Scilab. You are welcome to check it on your own as you go. But what I get on this is the answer of alpha, right, comp, which I just put a P, is 2 to the minus 10th, and alpha for my communication, I also picked it 2 to the minus 10, so that's how that worked out. So yes, it's not any surprising mystery. I picked these to give me what I felt were at least nice looking numbers on them. And there we go. Now we've got our setup on this, and we're going to now want to figure out how to solve our problem. So here we go. Let's bring in our next page of memory. So we'll do a memory swap here, maybe. Okay, so I pull that out and look, There we go. An amazing memory paging inside an analog machine. Okay, so now we say, great, I would like to now solve my problem. And my problem is I have something that I want to calculate, somewhere around an hour, which an hour is about, 60 minutes times 60 seconds. And there we go. So I've got 60 squared. So that's about 3,600. And I've got about anywhere from 3,600 up to about 1.5 of those, which would get me up to 5,400. Now I look at that and I go, okay, everything's all kind of powers of 2 based, so it'd be nice to pick a power of 2 and make my calculations a little simpler since I'm solving this by hand. So I'm going to try to solve this whole thing and make it done in 4096. It fits nicely within that range, kind of on the lower end. You always want to be a little bit optimistic anyway, because it will never be that good in real life. So try to get something that's kind of better ranged. This is just 2 to the 12th. So I now have a reasonable time period in an easy to calculate way since I'm having to do this by hand. Okay, so now we go through and solve this. So I now know that I want 2 to the 12th to be my time, and that I have 2 to the minus 10th. That's my alpha comp times, and then n was 2 to the 32 times, and log of that is 32. That's n log n over p, which I'd like to solve for, plus 2 to the minus 10th times, I've got 2 to the 32 over p. Both these have p. I pull it out to the other side, and then I get divide by this. So that gives me 2 to the minus 22 times 2 to the 32 times 32 plus 2 to the minus 22, which again is that 10 and that, times 2 to the 32. So that gives me, I need 2 to the 10th times 32 plus 2 to the 10th times 1. And I can now add those up, which gives me 2 to the 10th times 33. And 2 to the 10th is about 1,000. And a little bit over times 33. So I need somewhere around 33,000 computers to solve it in that about hour or so. Now, some other things worth noting is every time that I can double the amount of time, since proportional to p, they're inverses of each other. If I get twice as much time, I can use half as many processors. So if you look at that and you went, oh my goodness, 33, 35,000 processor, whatever that's going to work out as, somewhere in that ballpark zone, is way too much for me. We can only afford 1,000. Okay, well, great. It's 1,000. That's 2 to the 5th. So you want to cut down somewhere around 2 to the 5th. You've got to let me kick up my time by 2 to the 5th. So your hour is going to turn into like a day and a half, or a day and some change. So if you're willing to let me go a day and a half, I can cut it down to 1,000. You can now trade these things off. The other thing that reasonably you would also consider doing here is considering a better algorithm that goes on. And you might say, well, FFT is as good as it gets. And yes, that's true, but there are ways to get faster FFTs. For instance, if you can exploit structure, like for instance, sparsity, if there's not a lot of non-zero values, or other nice type of patterns within your code, you can get algorithms that take better advantage of it and therefore might work out nicer. Other things that also can become very important inside them is how well these things fit inside cache, so I can cut down cache misses, which would then change my alpha computation or alpha communication if I get a better transmission setup or things of that sort. So we can look at all these type of values to see what can go on. I can also consider adding extra memory into my system and so on and so forth to try to make this more efficient as it goes. So in any case, this gives you kind of a rundown of where we could do it. We've got a quick way to be able to ballpark it by taking some data samples. And again, I'd take a pretty decent number of samples if it were me. So hopefully this has helped you out. I think that gives you a pretty good idea of what I would like you to know from here. So try a couple examples yourself. There are some in my online notes. And good luck.